So we are solving our third problem in which a jogger loses its energy with the rate of 3000 watt in the days of winter at temperature of 5 degrees Celsius. Its body temperature is 30 degrees Celsius. But in summer days, ambient temperature means environment temperature is 28 degrees Celsius and its body temperature is 35 degrees Celsius and relative humidity is 45%. So we need to find the rate of evaporation in which its body sweatening and so we need to find the rate of evaporation of sweat in the warm days, and second we need to find the rate of total heat loss per unit time during the warm days. So we will firstly write all the given data. So firstly we will collect all the given data, and body temperature is 35 degrees Celsius and relative humidity, which is psi humidity in winter is 45, and we are given with the momentum diffusivity mu as 1.6 into 10 to the power minus 5 meter square per second, 2.3 into 10 to the power minus 5 meter square per second, and the latent heat of vaporization, which we will represent with L, we have given the value of nu and dV as previously we have seen. So we will directly take all the values. 1.6 into 10 to the power minus 5 and the value of dV is 2.3 into 10 to the power minus 5 and it comes out to be 0.69. So we get the value of Schmidt number, which we will use in previous steps. Now we have a Chilton-Coulomb analogy for heat and mass transfer. Each term S means Stanton number for heat transfer is defined as H by root number to the power 2 by 3 and Schmidt number for Stanton number for mass transfer is defined as K Kc by Vc. Here Kc is mass transfer coefficient and Vch is characteristic velocity. Schmidt number to the power 2 by 3. Here these characteristics and temperature difference is 35 minus 28. By calculating this, we get the value 0 watt is equal to 0.84 kilowatt. K, we need to find Kc into ACS and we don't know the value of Cosec. PR and SC we know by the given data. So here we will finally get the variation of sweat at the surface of the body of the jogger. So by using the formula of CAS is equal to PA saturation by RT, we will come to know the value of concentration. So the value of saturation is 1 by R, we know 3 1, and temperature is stated value of concentration 4 8 1 we do. So as we know, the humidity is 45% as given. So the maximum that can transfer through the body of a jogger to the atmosphere is 45% of the saturation value. So we will multiply with this factor. Ca is 0.45 into CAS. There's a difference which we know currently in summer days due to loss equal to Q1 plus Q2, which is 5.724 plus 0.84, which comes out to be 6.5 kilowatt total heat released or lost. So further we are moving to solve our next problem. In this problem, a plane is moving above 10 km height from the Earth's surface, and in this condition, the temperature is minus 50 degrees Celsius and the pressure is given 26.5 kilopascal. And the further data which is given, we will write on the board. Given data, we are given with the temperature of minus 50 degrees Celsius at the height of 10 kilometer above surface. And the pressure at those conditions is 26.5 kilopascal. And the value kg kilomole. And we are given with the velocity of plane as 800 kilometer per hour, which we will convert into meter per second. So we get the value as 222 meter per second. So from here we need to calculate the heat transfer coefficient of the plane wings. So further we will solve the solution part of this question. Okay, we have left with one more data which is important for the question. We will write it is friction coefficient of heat transfer of wings. So we will end up with the given data and we will further move to solve the solution part of this question. Here we are going to discuss the solution of this question. So firstly we need to find the density of the air at minus 50 degrees Celsius and at the altitude of 10 kilometers. So density is given as rho is equal to Pm average by R. We have all this following data, so we will put in this formula and get directly the value of density. So we find it as 0.4123 kg per meter cube. We will keep this in box. Now we have the data of Prandtl number. We don't written at the given part, so we will write here, which is 0.744, and for using so the Prandtl number is given as 0.744, which is not equal to 1. So we will use here Chiltern-Coulomb analogy. By using Chiltern-Coulomb analogy, we will find the value of heat transfer coefficient. So we have the formula of Chiltern-Coulomb analogy as Cf by 2 Stanton number of heat transfer into Prandtl number to the power 2 by 3. So we need to find here firstly we will put all the formulas like Prandtl number, we have the value of Stanton number, we have the value of Prandtl number, and we also have the value of means friction coefficient. So we will expand this formula. H rho Cp into V Ch into Prandtl number to the power 2 by 3. So we are given with the values of velocity, Cp, and here we find the values of rho. We have the value of Cf and Prandtl number. So by putting all the values, we can easily find the value of heat transfer coefficient. So firstly, we will put the values in this formula. Cf is 1.0016. We have taken this value in the given part, so we will directly take these values from there. H by rho. Rho is 0.4123 into Cp 999 into velocity 222.22. We have calculated these values in the given part, and the value of Prandtl number is 0.744 to the power 2 by 3. By calculating this, we get the value of heat transfer coefficient as 89.1588. The
Whatever we did.
means the unit of this is water per meter square Kelvin. By this, we can conclude this is the answer of this question. So now we are going to solve our last question, which is for a temperature difference between surface and environment. So the temperature of the plate, flat plate, is 120 degrees Celsius, and the temperature of ambient or environment is 20 degrees Celsius. So the heat is transferring from flat plate to the environment. So we have to find the rate of heat transfer from the plate to atmosphere. So for that we have some given parameters. So we'll write those parameters. So yeah, we are going to write our given parameters. So we are given with the area of the flat plate, which is 0.0. Sorry. It is 0.2, not 0.0. 0.2 into 0.2. These are the dimension of the flat plate. So by this we get the area 0.4 meters square, and we are given with the velocity of the air which is flowing over a flat plate. Air velocity, which is 14 meter per second, and the environment temperature is given as 20 degrees Celsius. And the temperature of the plate is 120 degrees Celsius, and the drag force is given 0.07 Newton. So yeah, so now we will proceed to the solution, and here a value of Prandtl number is also given. Prandtl number is 1 for this case. Solution. So now we will discuss how we'll proceed in this solution. So firstly we need to calculate CF, coefficient of friction. For that we will use the formula of drag force, which we know is half rho u infinity square into CF into area. We know the value of density, we don't know the value of density and the value of CF. So firstly we will calculate the value of density of air density. We will calculate here rho is equal to PM by RT. Pressure condition is 1 atm, which is 1.01 into 10 to the power 5 Newton per meter square, and average molar mass of gas is 29 kg per kilomole, and we have R is 8.314 joule per mole Kelvin, and we have last temperature is 293 Kelvin. By putting all this value in the formula, we get the value of density as 1.204 kilogram per meter. This we will use in the formula of FD. So here by putting the value of U infinity, we know the U infinity as 40 meter per second. Yes, it is 40 meter per second. It is air velocity, and we know the area, we know the FD and rho. So directly we can from here we can calculate the value of CF. by rearranging all the terms, FD divided by rho V infinity square into A. Yeah. So from here we will calculate the value. We will put all the values of parameters we know. 2 into FD is 0.075 divided by rho is 1.40 square into area we know 0.04. By calculating this we get the value of CF as 1.94 into 10 to the power minus 3. So this is the value of CF we get. From here we will use the formula of we will use Chilton-Corbin analogy by using Chilton-Corbin CF by 2 is equal to standard number for heat transfer into Prandtl number to the power 2 by 3. We know Prandtl number equal to 1. So this term is directly standard number for heat transfer into 1, which is same as standard number for heat transfer. So we will put the value of CF here 1.94 into 10 to the power minus 3 by 2 into, and we'll open the formula of standard number for heat transfer to H by rho Cp into Vch. We know the value of Vch, which is velocity of air, and the heat capacity and density. So from here we will calculate the value of H, which comes out. We know the value of H and area and delta. I guess I have to put all the values so that you guys will be pretty clear. Yeah. So the value of H is 11.775 and the value of area we know 0.04, and the temperature difference between the flat plate and air is 100 degrees Celsius. So by calculating this, we get the value of heat as 47.3 watt. It is okay, it is fine, just a little bit mistake on writing. Yeah. So this is the answer, final answer of this question. So we are I am concluding this with the answer. It shows this much heat is transferring from the plate in the environment because of temperature difference in the form of heat. So